Hey everybody, today's video lesson we're going to focus on how to use the equilibrium expression that we developed in the previous video lesson. I'm going to show you the basic kind of mathematical calculations that surround equilibrium. Okay, so here's an example problem. We have a chemist who places gaseous hydrogen bromide, HBr, with a concentration of 2.1 molar into a sealed container. Okay, so we're starting off with a sealed container with nothing but HBr gas in here. Okay, so what's going to happen is this HBr gas is going to undergo decomposition, and it's going to break down into hydrogen gas and bromine gas. So as a result of doing that, what happens is every time two of these HBRs break down, they make H2 and also Br2. Okay, so we make these two gases every time. So two of these goes into this and this. All right, so as that happens, we want to do is determine the concentration of the H2 and Br2 after the reaction has gone to equilibrium. Okay, so if we think about this, since we're starting with the HBr and we make the H2 and the Br2, we want to see how that plays out. And we need to look at this at equilibrium, not initially, but when we get to equilibrium. So we think about this, we can start with initial amounts of the hydrogen bromide, and what happens is that breaks down into those two gases. Well, if we think about that, if I start with this, I'm going to end up with X amount of this and X amount of the bromine, right? So what happens is whatever the amount of bromine is equal to the hydrogen. So our concentration of hydrogen at equilibrium is going to be equal to the concentration of the bromine at equilibrium. Okay, why is that happening? Because every time hydrogen bromide, two of these break down, what it's going to do is it's going to make one H2 and another Br2. So this is made, and then this is made. This is made, and this is made. So we're creating these at the same rate is what we find. These are good. They will be equal to each other, and that's important because when we look at trying to solve this, we're going to have to use that idea to figure this out. So what are we talking about? Well, since we're at equilibrium, we're going to use the K expression. Remember, K is equal to concentration of the products over reactants. So therefore, I can write the K expression for this is equal to concentration of the hydrogen times the concentration of the bromine over my concentration of HBr squared. Don't forget to bring the coefficient down. A lot of students forget that and miss that part, so don't forget to double that, or in this case, bring it up to an exponential value. All right, so we know what K is. Now, what does K tell us? Well, K tells us that, yes, we do start with some of the hydrogen bromide, and some of that hydrogen bromide will be used up. But here's the trick, is if this is really, really small, are we really shifting very far to the right? Remember, what does K tell us? K tells us how far to the right the reaction is going to sit at equilibrium. So when we produce the products, the HBr and the H in the HBr, the hydrogen and the bromine, we do have to lose some of this, but we're not going to lose a lot of it at all. This reaction is going to shift to the right very, very small. You're going to get a little bit of products, and this reactant is pretty much going to stay. This reaction dominates and controls the reactants. How do I know that? Because K is really small. Since K is a small value, that means I'm going to have a lot of my reactants and a very, very little bit. We have a lot of reactants and a real little bit of the products. Okay, so what that means is that the concentration of the hydrogen bromide is going to be the same. It will not change in this reaction. All right, so my concentration of HBr is going to stay the same. I know that these two are going to be some value x that I'm going to substitute into the equation, and I'm going to solve for K. So let's go ahead and do that. K is equal to x times x for the hydrogen and the bromine over, on that point 2, let's do 2.1. And it's 2.1 squared. I can drop the molarity out because K has no units, so I don't really need to worry about that. I'm going to make this x squared over 2.1, which would be 4.41 on the bottom when we square that. And I'm going to set this all equal to the value of K, which is equal to 5.8 times 10 to the minus 18. So it's going to leave me with x squared, and x squared comes out to be, if I multiply these two out and I bring the 4.41 over, and that's going to be equal to 2.56 times 10 to the minus 17, and that will leave me with x by taking the square root of both sides, and the square root of that is going to leave me with 5.06 times 10 to the minus 9 molar, and that would be equal to 5.1, because I have to do two significant figures because of my k, and it's equal to 10 to the minus 9 molar, and that is my concentration of the hydrogen, and it is also equal to the concentration of the bromine, and that would be my answer. So I'm going to just use this equilibrium expression. I'm just going to be plugging in information. I just got to be careful that I'm doing this at equilibrium. So when I talk about the problems, everything should pertain to equilibrium. All right, so let's take a look at one more. All right, for this one here, what we're doing is we are chemist is going to measure. So chemist measures the equilibrium concentrations of H2 and Br2. So this is different. We're starting with these at equilibrium, and they measure those values at equilibrium. Okay, using the reaction below to determine the concentration of HBr. So again, we're going to use K is equal, since everything is at equilibrium, H2 times Br2, the bromine, over HBr squared. Okay, so I'm going to always write this out. A lot of students, what they tend to do is they skip this part and they just plug right in. I would recommend that you, strongly recommend that you write this out, because you want to make sure you don't forget that square. Got a lot of students that will forget that square in here when they just write and plug numbers in. Alright, so what I'm doing is I'm solving for, what am I looking for, is I'm looking for HBr in this problem. That's what I'm looking for that quantity. Alright, so I'm going to solve for that. And if I solve for that, my equation is going to be HBr is equal to the concentration of, let's see, this is going to be brought over here, so it's going to be the square root of H2 times Br2 over K. That would be the equation. So I'm just rearranging this and solving for HBr. That's the equation that I'm going to use for this problem. So I'm going to plug everything in, and then I'm going to solve it. Okay, so HBr concentration is equal to the square root of, and I'm going to plug in the numbers that I have here, 4.19. Now the question is, why are these different? In the last problem, we saw that these two numbers were exactly the same. Well, maybe there was extra hydrogen added. You know, maybe there was some other situation. Well, we don't need the n. Let's get rid of the n, because we're doing equilibrium, and the equilibrium is going to have no unit. What is the unit going to be for this? It has to be molar. So make sure when you're dealing with concentrations, you put a unit. If we're dealing with K, we're not going to have a unit. I'm not going to put a unit in here because it's not going to work out mathematically, so it's not really important to put it in there. So 2.19 times 10 to the minus 8. I'm going to do that, all of that over 5.8 times 10 to the minus 18. All right, if I simplify this, I'm going to find that my concentration of the HBr is 1.26 molar. And that would be HBr hydrogen bromide. And that would be my concentration. Now let's think about this. What did we say earlier? K is really, really small. So should we have a lot of HBr, or should we have a little bit of HBr when we get to equilibrium? Well, based on this constant, I should have a lot more reactants than I do products. This is a reactant. So therefore, if we take a look at this, 1.26 is a lot greater than 4.19 to the minus 10. 2.19 times 10 to the minus 8. So again, it makes a lot of sense. It matches what K is telling us. So you might want to get a good intuitive idea of what K means. Let's just look at that previous problem one more time. Remember that we said that the K expression tells us that they're favoring the reactants. So what is my concentration of the hydrogen and the bromine in this problem? 5.1 times 10 to the minus 9. Very, very small number compared to the large 2.1. Again, that's not very large, but compared to this one, it definitely is. All right, and that's the general basic strategy that we take for dealing with equilibrium expressions. We'll practice this in class a little bit more, and I'll answer your questions. See you later, guys.